Naive assembly is the simplest, most obvious approach to assembly. That's why it's called naive. The basic idea is that we start with a DNA sequence that has a 5' end and a 3' end. If we can identify another DNA sequence that has sufficient significant overlap with the first sequence, enough that we're convinced that they represent the same section of genome, we can stick them together. We then generate a contig that runs from the 5' end of the first read to the 3' end of the second read. In theory, this is an easy problem to solve, and it looks attractive in principle, but as we're going to see, it's a bit more complicated than that. We may, for instance, have an error in the overlapping sequence. This might prevent us from identifying an overlap between the reads. Thinking back to Dr. Tucker's lecture though, we might be able to use the reads quality scores to adjust our trust in that base call and allow the overlap for a non-matching base, if the base call quality is poor. There's also the question of how long an overlap needs to be to convince us it's real. If it's too short, we might wrongly match a whole load of reads that don't really sit together on the genome. Too long, and we might not match any reads, especially if there are a lot of base call errors. So how long an overlap do we need? Well, we've got a DNA alphabet of 4 bases, A, C, G, and T. Suppose our reads overlap by some number of bases, and we'll call this number K, then how many different sequences are there of length K? If there are only a few different sequences of length K, we're likely to see a lot of those sequences in the genome by chance, if it's a long genome. This will make it difficult to select only correct overlaps between reads. But if there are many different sequences of size K, we'll not see very many of them in a genome by chance alone. We'll then be more confident that the overlap correctly joins 2 reads that represent the same point on the genome. How can we calculate the number of different sequences of size K? Well, there are 4 choices of base at the first position, A, C, G, and T, 4 at the second position, 4 at the third, and so on and so on. So for an overlap of K bases, there are 4 to the power of K possible sequences. If K equals 3, and we call sequences of length 3 trimers or threemers, there'll be 4 to the power of K, or 4 cubed, which is 64 possible sequences. We'd therefore expect to find any given threemer, on average, once in every 64 bases of the genome. We'd find a lot of the same threemer in a bacterial genome of 6 million base pairs, so we'd probably end up matching a lot of reads that don't belong together if we chose this size of K. So we definitely need to look at a larger overlap. If K is 8, there'll be 4 to the power of 8, which is 65,536, possible different sequences. We'd expect to find any given 8mer on average once in every 65,000 bases or so. This sounds like a lot, and you might think this would help avoid incorrect overlaps, but E. coli's got about 5 to 6 million base pairs in its genome, so even with 8 bases in an overlap, we still expect to join non-overlapping sections of the genome about 100 times for every read. 8 is still too short to be useful. For K equals 20, there are 4 to the power of 20, which is about a million, different possible sequences. With this many sequences, we'd expect to find any given 20mer about once in every billion bases or so. That's rare enough that each overlap should only occur once by chance in a random genome of the same size as a bacterial chromosome. We should then expect that each overlap is unique and be confident that the 2 reads come from the same part of the genome. So we might expect that for a random distribution of bases in the genome, we should be convinced that when we see a 20 nucleotide overlap between 2 reads, it's unique, and we ought to be able to combine them into a single contig that really exists on the genome. But there's a big problem here.